Last time we were talking about two-nucleon effective field theory. So this was a non-relativistic field theory. Both of these terms here in the action were the same size. They were the same relevance. And we talked about that last time. So in HQET, it would just be the first term. But in this case of two nucleons, we actually need the kinetic term as well. And both of these terms are equally important. And that basically means that in this type of system, the time derivatives and spatial derivatives are counted differently. But you can organize the field theory using equations of motion so that these are just local operators with spatial derivatives. So you basically deal with the time derivatives once and for all. And you could always use equations of motion to eliminate them there. And so you just have really this one time derivative. This theory is particularly simple if we neglect the relativistic corrections. And that's because it's a non-relativistic field theory, we just have these bubble diagrams. And they're just contact interactions, so they all decouple from each other. So at end loop order, we can just write down what the loops are. We talked about the fact that in terms of power counting, things could be a little subtle. And that was related also to a power divergence that occurs in this diagram. And we could track that power divergence by using particular schemes that gave this extra mu r term. And I won't repeat all that story, but that led us to adding a finite counter term to this bubble diagram to track the power law divergent term. And that allowed us to come up with a power counting that would take into account systems where the scattering length is large, or in particular, the scattering length times momentum is greater than 1. And in these two nucleon systems, that's exactly the scenario that we're in. So what we then had was a power counting that assigned the very first operator to scale like 1 over a power of momentum. So not like a 1 over a power of a large scale, but actually 1 over a power of something small, the momentum that we're interested in studying. So it's enhanced in the power counting that we wanted to adopt. And that meant basically that you had to treat this one coupling, C0, non-perturbatively. You summed it up to all orders. So the term here comes from adding up all the diagrams with any number of bubbles, and that all give this first term. And then the rest of the couplings are treated perturbatively, the higher derivative term. So a term C2, which comes with a grad squared, and that gives this extra p squared in the numerator here, gets treated perturbatively, and there's this term, and then there's higher terms, and that's how we could organize this theory. And this sums up all these powers of a times p, these denominators that I'm showing you there. So what I want to do for the first part of today is just really continue with this effective field theory and talk about a few more of its features. First, I want to start with symmetries, and then we'll talk about something called the deuteron. Yeah?
Just a question about the relevance of the kinetic term.
Yeah.
So other than getting a pinch singularity in your integrals, is there I don't know, a more power counting friendly kind of argument for
yeah, so you can think about it like really what we're doing here is non-relativistic quantum mechanics. And if you think about non-relativistic quantum mechanics, you think about like the virial theorem, you're used to thinking about the fact that kinetic energy and potential energy are equally relevant, right? So from a physics standpoint, if I didn't want to talk about diagrams, or I just wanted to make a physics argument for why that would be the right thing to do, I could simply tell you, I want non-relativistic quantum mechanics at lowest order. This is a system with two heavy particles, and that's what the physics should be. If you start with the wrong theory, then you run into problems, and that's kind of what we saw. If we started with an HQET-like reasoning, then we see this pinch singularity, which is resolved by the kinetic term.
Okay, why is it that non-relativistic quantum mechanics has the form that it does then?
Why does non-relativistic quantum mechanics have the form that it does?
Yeah.
So think about it from the following point of view. So when we just had this term, what was the particle doing? When we just had the partial t term, it's like a source. We had a single source sitting there, and we were interacting with it with some light stuff. That was HQET. Here we have two sources, and they have to interact with each other. And the problem is that two sources interacting with each other, really the kinetic energy becomes a relevant thing. It's not, I mean, It's actually a little more subtle than that. If you really want to go into it in a gauge theory, there's sort of situations where these two heavy sources act like two heavy sources, like HQET, and there's situations where they wiggle. And the situations where they wiggle are exactly the things that the Schrodinger equation is giving you. If you like, so to say it precisely, the potential between the two heavy particles, for the purposes of figuring out that potential, you can treat them as static and fixed. But then once you have that potential, these bubble diagrams are kind of the way in which that potential gets iterated into the thing that you would get from solving the Schrodinger equation. So solving the Schrodinger equation, you're effectively treating the potential to all orders in this series, exactly this bubble series. And when you solve that, you need to include the kinetic, this grad squared over 2m, for the same reason that it's a relevant thing to include in quantum mechanics. OK. Good project choice. I urge you. No. OK, so let's talk about some of the symmetries of this theory, which are kind of interesting. So the first one is that this theory actually has a non-relativistic conformal invariance. So what is a non-relativistic conformal invariance? So this is an extension of the Galilean group rather than the Poincaré group. So we have the usual translations. We have rotations. We don't have Lorentz boosts, but we do have Galilean boosts for a non-relativistic system like this. So what would those be? So under a Galilean boost, time is not changed, and the spatial coordinates are changed. And then there's additional generators that you have in this conformal, for a conformal invariance. One is a scale transformation. There's one generator. And the way that the scale transformation works is as follows. You rescale the coordinates by some, let's call it e to the s, but you have to rescale time differently by e to the 2s. And the reason that you have to do that is exactly because these two terms should be treated the same. So you have to rescale time twice as much as you rescale the spatial derivatives, if you like. So that's what gives rise to the 2 there. And that just goes to the heart of sort of counting time and space differently. And then finally, there is a conformal generator. And there's actually only one generator in this non-relativistic case. And basically what this generator corresponds to is a shift of inverse time and then a corresponding change to the coordinates. And if you take all these things together, it's actually something called the Schrodinger group. And the theory we've been talking about actually has this non-relativistic conformal symmetry. If A goes to infinity. So I'm not going to spend a lot of time talking about this, but just to give you some of the ideas of what's going on. If you look back last time at our solutions for this coupling constant, and you take A goes to infinity, that's a perfectly smooth limit. You can do that. And then the coupling C0 of mu has no free parameters. It's just given by 4 pi over m mu. And that corresponds to sitting at this, what we last time saw was a fixed point of the beta function. And at that fixed point, there's an enhanced symmetry, which is this conformal symmetry. And basically, what you can show is that if you scale here mu, just like it was a momentum, so mu goes to e to the s mu, then the Lagrangian is scale invariant. Maybe in my notation up there it would be minus S. Okay, and that is basically kind of the same thing as making it into a relevant coupling. Once it's got no free parameters, then you can sort of see that if I have a certain scaling that makes the free theory Schrodinger invariant, which is, so the Schrodinger group is the symmetry group of the free Schrodinger equation. So just this term and this term. Then the question is, what interactions can you add that would preserve that symmetry? And I'm just telling you that in terms of just the scale transformation, you could, if you're able to scale the coupling in some way, in particular to make it a relevant interaction, then that will make it a scale invariant theory. And so the ability to scale this coupling because you scale this mu allows it to be a scale invariant theory. It's a little harder to see that it's conformal, but you can work that out too. Scale invariant theories tend to be conformal invariant, and the same is true of this non-relativistic conformal invariance. So if you sort of add up the bubbles that we were talking about, then you find in general an amplitude, which is this thing that has a square root. But if I'm not particular to what frame I'm in now, if I just write it for a general frame, before we wrote it for the center of mass frame, now let me write it for a general frame. Then it would look like this. And that thing goes like 1 over p, so it has, and again, e's scale differently than p's, so this thing has the right scaling for a scale invariant amplitude. And it turns out if you do work out the conformal transformation, it's also conformal invariant. And I'm not going to go through that, but I've posted a reference to show you how it works. And basically what this leads to is a cross-section, which is 4 pi over p squared, which is the scale invariant version of a cross-section where the cross-section units are just set by p. So there's no other scale in the problem. Okay, so that's kind of interesting, and one can make some predictions with that. This is actually something that's also, investigated these days, both from a string theory point of view as well as in cold atoms. So the conformal symmetries are always fun to play with. There's also another set of symmetries that this theory has in this limit, which is also interesting. And that is, like HQET, there's an enhanced spin symmetry. This time, the enhanced spin symmetry comes about by combining spin and isospin. And this is a symmetry that's known as Wigner's SU4 symmetry. So Wigner, I don't know how many years ago, noticed, long ago, Wigner noticed that nuclei tend to have a symmetry, which is a combination of spin and isospin into a full SU4. And we can understand actually partly where that comes from this effective field theory. So what is this SU4? Think of it as just transforming the nucleon field under a way where you could mix up the spin and the isospin. So if sigma is for the spin, tau is for the isospin, then some combined transformation where I can mix up the mu and nu's would just have some set of generators where I label them by mu and nu. Sigma mu here is 1 comma sigma vector, tau nu, 1 comma tau vector for the isospin. If you just take the 1 from both of them, that's baryon number, and that is what would turn the SU4 into a U4, so you can remove that generator if you like. So there's a U1 as well, but the non-trivial part where you take either this or that or both is an SU4. So we can think about this symmetry with our theory if we write it as follows. So take the interaction terms that we've been talking about and write them in a slightly different basis. Just take these 2-to-2 scattering terms, which had no derivatives, and I'll write them in a slightly different basis. Before, we wrote them in sort of the physical basis, where we had 3s1 and 1s0. That's what we did last time. But there's other possible bases, and I can write them in this basis, singlet-triplet basis. And the advantage of this basis is this thing here is just SU4 symmetric. And if you want to write down the relation to the previous basis, you can work that out. I just tell you what it would be by writing down what the coefficients here are in terms of the ones we had before. So if we go back to the basis where we had coefficients for the 3s1 channel and the 1s0 channel, then this C0s becomes this combination, and C0t is this combination. Now in nature, so one way you could have SU4 symmetry would just be for the scattering lengths, the physical parameters C01s0 and C03s1 to be equal. But in nature, they're not equal at all. In fact, the scattering lengths have different signs. There's no sense in which they're equal. So what is the sense in which we have this symmetry? The sense in which we have this symmetry is the fact that if the scattering lengths are both infinity, then both couplings are just this. So the fact that the scattering lengths have different signs but are both large makes them close to this fixed point, which then gives us symmetry. Okay, so because of what I just said, for a goes to infinity, C0s, which is sort of equal, some symmetric combination of these two that become equal, would just become 4 pi over m mu. And this is for a1s0 and a3s1, both going to infinity. This one's minus infinity. And then the triplet one, if we just work out what it is from our formulas for those other couplings, work out the combination from formulas we had last time, and we see that as the a's go to infinity, this coupling vanishes. Okay, so when we're in the limit where both of the couplings become equal, or if we use this basis where this coupling becomes 0, we just have this n dagger n squared operator, then we have this SU4 symmetry. On one of the problems on this new problem set is to think about to what degree you still have that symmetry when you think about higher body operators, 3-body and 4-body. And there's actually some very nice little group theory arguments where you can basically figure out to what degree you have that symmetry in the higher body operators. It turns out that it's also present there. And that is one way of thinking about why Wigner's symmetries exist in nature. It's not that we're, in any sense, having scattering lengths that are similar in these two channels, but since they're both large, we're close to these fixed points which have this symmetry. Okay, so it's like HQET in a sense, where we didn't have heavy quark spin symmetry when the masses are finite, but if the charm mass and the B mass are both infinite, then there's this new symmetry that pops up. It's kind of like that. Okay.